Welcome to the problem solutions for Chapter 2, Classical Polarization. The first problem was just asking you to find the intensity change, or the change in intensity, between the input and output vector polarization. And so basically, you just needed to find the output polarization, which is just done by multiplying the Jones vector for the optical element that this problem used, and the input vector, which was left circularly polarized. And then you just compare the ratio of these two intensities, so the output intensity versus the input intensity. And if you go through and find this, then you get 1/2, which is independent of theta. And so if you're still not sure why I did this or how I got a value for this, it's because the intensities are proportional to the magnitude of the polarization vector squared. And so all I have to do is find these things squared and then divide those. Because if these had any other constants out here that make them proportional to intensity, they cancel out when you divide them. And so all that matters are the polarization vectors. For problem 2, it's just looking at 3 sequential wave plates and seeing what's the Jones matrix for them. And so that's created by multiplying these matrices here. So you first multiply 2 and 1, and then 3 and the new one. So 2 times 1 would be this. And then you have 3, which is still here. So, and then when you times 3 times the 2 times 1, you get this new matrix, and then you can factor out a 2. And then the problem also asked to find what the output Jones vector is, and it's this. Now for problem 3, it was just asking to prove that right circular polarization becomes left circular polarization after passing through a half-wave plate. This is the same thing as asking mathematically to find an eigenvalue. So you're basically saying that this input into the wave plate system gives just a scaled output of the left circular polarization. And because it's just a phase shift that's unimportant, we know that the eigenvalue delta must have a magnitude of 1. And so we set this up, solve for, or we set this up and then simplify the system. Keep going. You can divide this system, this element out, pull it out here, and you get a 1, divide here. And then you can change this into an e to the angle representation using Euler's formula. And it simplifies like this, where you actually, so you get 1 over negative I, which just simplifies to 1I. So you can see here we have the left circular polarization vector, and then we have some constant here. And this does have a magnitude of 1, as you can see here. And so this is the eigenvalue, and we've just proven that there does exist an eigenvalue such that the magnitude of it is 1, and the Jones matrix times the right circular polarization vector is equal to just that eigenvalue times the left circular polarization. And for problem 4, it's just asking if it affects magnitude, and you find that it doesn't actually affect magnitude. It just gives it a phase shift, and it doesn't affect magnitude because you just have the identity matrix. And so yeah, these are the problems. Next video that I release will be on chapter 3, where we start talking about quantum mechanics of polarization.